Imagine this. Somewhere to 100 light-years away, there is a planet that can be the future home of humanity. TOI-700, and one of the most promising exoplanets ever discovered, is located in the habitable zone of its star, that magic region where conditions can allow the existence of liquid water, an essential ingredient for life as we know it. But can he really shelter human life? This question echoes urgently as we face global crises such as climate change, overpopulation, and the unsustainable exploitation of land resources. TOI-700, and orbiting a red dwarf star called TOI-700, has caught the attention of space scientists and enthusiasts since its discovery. With approximately 95% of Earth size and a stable orbit, this exoplanet offers conditions that could be suitable for sustaining life forms. However, there are still many unknowns. The atmosphere of the planet, its chemical composition, and even the possibility of protective magnetic fields are questions that need to be answered before we seriously consider human migration there. Today, we will explore this fascinating possibility and find out if TOI-700 and can be our next border in space. Is this distant planet just a mirage of hope, or a real opportunity to ensure the survival of humanity? Throughout this video, we will plunge into the characteristics of the TOI-700 system, the technologies necessary to achieve it, and the challenges we would face when trying to colonize it. This journey is not just about science. It is about imagining a future where humanity is no longer limited to a single planet. We are facing a new era of space exploration, where dreams once reserved for science fiction are becoming tangible possibilities. But to turn these dreams into reality, we need to understand the obstacles that await us and what really means to expand our presence beyond the Earth. TOI-700 is a red dwarf star located in the constellation of Dorado, about 100 light-years from Earth. Although it is smaller and colder than our Sun, this star has caught the attention of scientists due to its fascinating planetary system. So far, 3 exoplanets have been confirmed orbiting TOI-700, TOI-700b, TOI-700c, and, of course, the most intriguing of all, TOI-700e. The latter, located in the star of the star, arouses special interest in its promising characteristics. This chapter presents the basic data about the system and explains why it caught the attention of scientists. TOI-700, and was discovered by NASA's TESS Survey satellite TESS Survey mission, which monitors close stars in search of periodic falls in brightness, a revealing sign that a planet is passing in front of its star. The exoplanet is approximately 95% of the Earth size, suggesting that it can be a rocky world, similar to ours. In addition, its orbit is perfectly positioned in the habitable zone, where temperatures allow water to exist in a liquid state, an essential prerequisite for life as we know it. But does this planet have the ideal conditions for sustaining life as we know it? To answer this question, we need to analyze other factors beyond its location in the habitable zone. For example, we still don't know if TOI-700 and have an atmosphere, and if so, what would be its composition? A dense and rich atmosphere in gases such as oxygen, nitrogen, and carbon dioxide would be crucial to regulating the climate and protecting the surface of harmful radiation. In addition, we need to consider the activity of the host star. Red dwarfs like TOI-700 are known to emit intense sunscreen, which can wear out or even completely eliminate the atmosphere of nearby planets. Another interesting point is the relative proximity of TOI-700 and in relation to the Earth. The distance of 100 light-years may seem immense, but in astronomical terms it is relatively close. This makes the TOI-700 system a priority target for future observations with advanced telescopes, such as James Webb Space Telescope, JWST. These instruments may analyze the atmosphere of the planet, looking for signs of water vapor, organic molecules, or even biosign, indirect evidence of life. Scientists are particularly excited about the potential of TOI-700, and because it represents a unique opportunity to study a planet that can share characteristics with primitive land. If humanity intends ever to expand its presence beyond the solar system, systems such as this will be crucial to our understanding of the necessary conditions to support life in other worlds. Each new discovery about TOI-700 and brings us closer to answering the fundamental question. We are alone at universe's The habitable zone is the region around a star where temperatures allow the existence of liquid water, essential for life. This magic track, often called Goldilocks zone, is neither too hot nor too cold, but perfect for a planet to keep conditions stable enough to support life forms. And this is exactly where I was, 700, and is, orbiting its red dwarf star at an ideal distance so that water can exist in a liquid state on the surface. This chapter explores as TOI-700 and fits this category and what is its unique characteristics. The orbit of TOI-700 and is relatively stable, completing a return around its star every 37 days. Although this seems incredibly fast compared to Earth's 365-day cycle around the Sun, the smallest brightness of the red dwarf means that the planet receives only about 86% of solar radiation that Earth receives. This balance is crucial to maintaining moderate temperatures, allowing liquid water, or at least the possibility of it, to persist on the surface. But what makes TOI-700 even more special? In addition to being located in the habitable zone, the planet is approximately 95% of Earth's size, suggesting that it can be rocky, similar to our planet. This puts it in contrast to other giant exoplanets or inhospitable worlds that do not offer the necessary conditions to sustain life. Its proximity to the Earth in astronomical terms, 100 light-years, also makes it a priority target for future observations, especially with advanced telescopes such as James Webb Space Telescope, JWST. Could this planet have oceans, atmosphere, and even alien life forms? These are questions we can't answer yet for sure, but there are reasons for optimism. If TOI-700 and has a dense atmosphere, it could help regulate the climate and protect any form of emerging life of harmful radiation. In addition, the presence of liquid water, combined with basic chemical elements such as carbon, hydrogen, nitrogen, and oxygen, could create the ideal conditions for the emergence of simple life forms. Some scientists speculate that planets like TOI-700 and may even house primitive ecosystems, such as those that existed on Earth billions of years ago. However, there are significant challenges to consider. Red dwarfs like TOI-700 are known for their intense star activity, including solar explosions capable of wearing or completely eliminating the atmosphere of nearby planets. If TOI-700 and does not have a magnetic field strong enough to protect its atmosphere, life as we know it would be virtually impossible. Also, even if the planet has liquid water, other conditions, such as the chemical composition of the soil or the presence of toxic gases, can make the environment hostile. This analysis leads us to reflect on the resilience of life in the cosmos. Even in the face of these challenges, the possibility of the TOI-700 and sheltering life, or at least conducive conditions for her, is exciting. Each new scientific discovery brings us closer to better understanding the mysteries of this exoplanet and other worlds that can share characteristics similar to that of Earth. TOI-700 and is often compared to Earth because of its size and position in the habitable zone. But what are the crucial differences? Although the exoplanet has approximately 95% of Earth size, suggesting that it can be rocky, like our planet, there are several variables that need to be considered before we claim that it is a second home for humanity. To understand whether TOI-700 and could really support human life or other life forms, we need to analyze factors such as gravity, atmospheric composition, and star radiation. This chapter analyzes factors such as gravity, atmospheric composition, and star radiation to understand how habitable it really is. Let's start with gravity. With a size close to that of Earth, it is likely that TOI-700 and has a severity similar to ours. This means that humans could walk on their surface without facing extreme challenges, such as very high gravity, which could crush our body structures, or very low, which could cause long-term health problems, such as bone loss. However, we do not yet know the exact mass of the planet which directly influences the gravitational force. A significant difference in this respect could completely alter the viability of survival. Now, let's talk about the atmospheric composition, one of the greatest mysteries of TOI-700e. We still have no concrete data about its atmosphere, but this information is crucial to determine if the planet can sustain life. A dense and rich atmosphere in gases such as nitrogen, oxygen, and carbon dioxide would be essential to regulate the climate, protect against harmful radiation, and allow biological processes. Without it, any attempt at colonization would be virtually impossible without advanced technology. In addition, the presence of toxic gases such as excess methane or ammonia could make the environment inhospitable to terrestrial life forms. Another critical factor is the star radiation emitted by the red dwarf TOI-700. Red dwarfs are known for their intense activity, including solar explosions that can release massive amounts of ultraviolet radiation and X-ray. These events could devastate any fragile atmosphere around TOI-700, and besides exposing their surface to lethal levels of radiation. Even if the planet has a robust atmosphere, it would take a global magnetic field strong enough to divert radiation and protect any form of emerging life. On Earth, our magnetic field plays this vital role, but we still don't know if TOI-700 and has something similar. Could we survive there without advanced technology? Probably not. Even if I was 700 and have a liquid water and an appropriate atmosphere, the challenges imposed by star radiation and possible hostile environmental conditions would make human life unsustainable without technological intervention. For example, pressurized habitats, radiation protection costumes, and life support systems would be essential to ensure survival. In addition, the absence of certainty about the chemical composition of soil and water increases the need for extreme preparation before any attempted colonization. However, this analysis does not completely eliminate the possibility of alien life on the planet. Life forms adapted to the specific conditions of TOI-700, and such as radiation-resistant extremophilic organisms or extreme temperatures, could have evolved in ways we can barely imagine. This perspective leads us to reflect on how life can be diverse in the cosmos, going beyond earthly limitations. Even if TOI-700 is promising, colonizing it will not be a simple task. Astronomical distances, technological limitations, and adaptation to the environment are just some of the obstacles that make this contract a colossal challenge. After all, we are talking about a planet located 100 light-years from Earth, such a vast distance that our current technology can barely conceive how to get there, the more a functional colony establishes. This chapter explores the main challenges we would face when trying to transform TOI-700 and our new home. Astronomical distances. The first major obstacle. The 100-year-old distance may seem close in cosmic terms, but in practice, it is a monumental barrier. To put this in perspective, the fastest space probes ever built by humanity, such as Voyager 1, would take millions of years to travel this distance. Even with futuristic technologies, such as nuclear propulsion or fold engines, still purely theoretical, reaching TOI-700 would be an unprecedented feat. In addition, sending human beings on this journey would require solutions to maintain live crews for decades or centuries, which raises questions about supplies, mental health, and even reproduction in space. Current technological limitations. Our technological progress is still crawling compared to what would be necessary to colonize a distant planet. Nowadays, our life support capabilities outside the Earth are limited to spatial stations such as ISS, which depend on constant supplies sent from Earth. Replicate these conditions in TOI-700 and would be infinitely more complex, as we cannot count on fast replenishment. We would need to develop self-sufficient habitats, advanced resource recycling systems, and robust technologies to deal with unknown environments. And yet, any technical failure could be catastrophic. Adaptation to the environment, an unknown world. Adapting to the specific conditions of TOI-700 would be another gigantic challenge. Even if the planet has liquid water and is in the habitable zone, we still know very little about its atmosphere, chemical composition, and climate. For example, if the atmosphere is rich in toxic gases, or if the soil contains hazardous elements, human survival would depend entirely on technology to create safe, artificial environments. In addition, the intense radiation of the red dwarf TOI-700 would require additional protection, possibly through armored domes or artificial magnetic fields. Sustainability and resources. Colonizing TOI-700 also requires us to think of long-term sustainability. How would we ensure access to food, drinking water, and energy? Does the planet have enough natural resources to support a human colony? If not, we would have to transport everything that we need the Earth, an impractical solution given at a distance. Alternatives include the creation of artificial ecosystems or the use of technologies such as 3D printers to make tools and materials on site. However, These solutions are still in the early stages of development. Are we ready to overcome these challenges? This is the question that echoes at the end of this analysis. Yes, we would face immense challenges, but they are not necessarily impossible to overcome. The history of humanity is marked by achievements that previously seemed unthinkable, from flying through heavens to exploring the depths of space. However, to conquer TOI-700, and we would need a coordinated global effort, massive investments in science and technology, and a fundamental change in our mindset as a species. Instead of competing for resources here on Earth, we would need to learn to cooperate to ensure our survival in the cosmos. Traveling to TOI-700 will require technological advances that are still beyond our current reach. Folding engines, light propulsion, or even autonomous artificial intelligence may be necessary to overcome the barriers imposed by the vastness of space. After all, we are talking about a distance of 100 light-years, a route that would take millions of years with current technologies such as chemical rockets. This chapter explores the hypothetical technologies that could take us there and answer the crucial question: when can we take this trip? Revolutionary propulsion, the first step. To reach TOI-700 in a viable time, say decades instead of millennia, we would need radically faster forms of propulsion than anything ever developed. One of the most promising ideas is laser propulsion, also known as solar candle. In this concept, a light probe equipped with a reflective candle would be driven by laser beams fired from the Earth or nearby space stations. This technology could theoretically allow speeds of up to 20% of light speed, reducing travel time to a few decades. However, building such powerful lasers and sufficiently large sufficient candles is still in the kingdom of speculation. Another intriguing possibility is nuclear propulsion. Thermal or fission nuclear motors could offer greater energy efficiency than traditional chemical rockets, allowing faster interstellar trips. There are already conceptual projects, such as the Orion project, which proposes to use controlled nuclear explosions to boost a spacecraft. Although it is a fascinating idea, it faces ethical, technical, and security challenges that have not yet been resolved. What about folding engines? Popularized by science fiction, these theoretical devices would work by folding space-time to allow faster travel than light without violating the laws of physics. Although Einstein's theory of general relativity suggests that this may be possible, creating such technology would require energy and exotic materials that we do not yet fully understand. For now, folding engines remain in the field of scientific speculation. Artificial intelligence and automation, build in space. In addition to new forms of propulsion, the colonization of TOI-700 will strongly depend on artificial intelligence, AI, and automation. Given as the time you need to get to the planet, sending humans directly can be unfeasible. Instead, advanced AI robotic probes could be sent first to explore the environment, build initial habitats, and prepare resources before the arrival of the first human settlers. These machines could operate autonomously for decades or centuries, ensuring that everything is ready to support human life as soon as we arrived. When can we make this trip? The short answer? Not so early. Even with massive investments and accelerated advances, technologies such as laser propulsion or nuclear engines are still decades to come true, and something as ambitious as folding engines will probably take centuries to be developed, if possible. However, small steps are being taken now. Projects like Breakthrough Starshot, which seeks to develop solar candles to explore nearby stellar systems, are examples of initiatives that can pave the way for future interstellar missions. But the question is not only when we can travel to TOI-700, but if we should. Before embarking on such a colossal journey, we need to solve our problems here on Earth, from environmental crises to social divisions. After all, expanding our presence through the cosmos will not make sense if we cannot preserve our own Christmas planet, one of the biggest unknowns about TOI-700, and is its atmosphere. If it contains oxygen, carbon dioxide, or other essential gases, this can determine its habitability. After all, the atmosphere of a planet is much more than just an invisible layer around it. It is the shield that protects against radiation, regulates the climate, and enables fundamental biological processes. Without an appropriate atmosphere, any attempt at colonization would be practically impossible without advanced technology. This chapter plunges into scientific theories about the planet's atmospheric composition and explores if we can breathe there, or we will need artificial habitats. What we know, and we don't know, about the atmosphere. So far, our understanding of the TOI-700 atmosphere is limited. Despite its promising location in the habitable zone, we do not have concrete data on its density, chemical composition, or even its existence. Preliminary studies suggest that rocky planets such as TOI-700 may have gases rich atmospheres such as nitrogen, carbon dioxide, or water vapor, but this still needs to be confirmed with more detailed observations. Instruments such as James Webb Space Telescope, JWST, are being used to analyze light spectra filtered by the planet atmosphere, seeking signs of specific molecules. However, these data are still partial and inconclusive. If TOI-700 has an oxygen-rich atmosphere, that would be a great resident of habitability, especially for terrestrial life forms. Oxygen is essential for human breathing and can also be a sign of ongoing biological processes, such as photosynthesis performed by similar plants or organisms. However, finding oxygen alone does not guarantee that the planet is suitable for us. Other factors, such as atmospheric pressure and the presence of toxic gases, such as methane or ammonia, also directly influence the viability of survival. Would breathing there possible? If TOI-700 has an atmosphere similar to that of Earth, with approximately 21% oxygen, 78% nitrogen, and traces of other gases, so perhaps it was possible to breathe directly on its surface. However, this hypothesis is highly speculative. Even if there is oxygen, it may be present in insufficient quantities or combined with harmful elements. In addition, atmospheric pressure plays a crucial role. A very low pressure could make our bodies unable to absorb oxygen properly, while very high pressure could cause severe health problems. Another probable scenario is that TOI-700 has an atmosphere incompatible with human life. For example, it could be dominated by carbon dioxide, such as Mars or Venus, or contain high levels of toxic gases. In this case, breathing directly on the surface would be impossible, and humans would depend entirely on artificial habitats or spatial costumes to survive. Artificial habitats, our plan B. If the TOI-700 atmosphere is not breathable, artificial habitats will be essential for any attempted colonization. These closed environments would replicate land conditions, providing purified air, temperature control, and radiation protection. Technologies such as air recycling systems, already used in ISS, could be expanded to support entire colonies. In addition, plant bioengineering adapted to local conditions could help create artificial ecosystems capable of producing oxygen and food. However, building such habitats on a distant planet has significant challenges. Transporting enough Earth materials would be unfeasible, so we would need to use local resources, such as minerals and water, if available. This would require advances in space mining, 3D printing, and robotic automation to build infrastructure even before the arrival of the first settlers. The atmospheric composition of TOI-700 remains an unknown fascinating. If we can confirm the presence of a dense and breathable atmosphere, this will open doors for direct colonization. Otherwise, artificial habitats will be our only option. Regardless of the scenario, the atmosphere of this exoplanet will be one of the decisive factors to determine if it can really become our new home. Before we arrived, is it TOI-700 and already houses life forms? Microbes, alien plants, or even advanced civilizations may be present in this promising exoplanet. After all, if the Earth is just an example of how life can arise in adequate conditions, why not imagine that TOI-700 can also be home to unique life forms, perhaps even smart? This chapter explores the hypothesis that we are not alone in the universe and that TOI-700 may be proof of that. Also, we will reflect on a key question. How would we react when finding extraterrestrial life? Microbial life. The first step. The possibility. It is more likely to be 700 and shelter simple life forms such as microbes. In our own planet, extremophilic organisms demonstrate that life can prosper in hostile environments, from deep thermal sources to arid deserts. If the exoplanet has liquid water, a stable atmosphere, and basic chemical compounds, such as carbon, hydrogen, nitrogen, and oxygen, microbes could have evolved to take advantage of these conditions. These organisms could be responsible for biological processes that release gases such as oxygen or methane in the atmosphere, offering detectable clues to advanced telescopes. But what if we find something bigger? Alien plants, for example, could have evolved to capture the fine light of the red dwarf TOI-700, developing unique pigments adapted to this specific environment. These ecosystems could be very different from ours, with biological cycles and interactions between completely new species. Discovering vegetation life in TOI-700 and would be a historic milestone, confirming that life is not exclusive to Earth. Advanced civilizations, a remote but fascinating possibility. What if TOI-700 and is already inhabited by an advanced civilization? Although this idea seems closer to science fiction, it cannot be completely discarded. Type 1 or 2 civilizations could have dominated their planet and a mother star, using technologies we barely imagined. Signs of industrial activity, such as heat emissions or artificial structures, such as Dyson spheres, could be detected by future observatories. Finding evidence of intelligent life would be a transformative event for humanity, redefining everything we know about our position in the cosmos. However, the absence of clear signs so far suggests that if there are civilizations in TOI-700, and they may be operating at frequencies or scales we do not yet understand, or perhaps they chose to remain invisible, silently watching while waiting for the right time to contact us. How would we react when finding extraterrestrial life? This is one of the most intriguing questions of space exploration. The discovery of alien life, whether microbial or intelligent, would have deep implications for science, philosophy, and even religion. Finding microbes could help us better understand the processes that lead to the origin of life, while the discovery of an advanced civilization could inspire both admiration and fear. How we would react depends on the type of life found and its intentions, if it is intelligent. If we find microbial life, the reaction is probably of scientific enthusiasm. It would be a validation that life is abundant in the universe and would open doors for new research on Biocene and habitability. However, the discovery of an advanced civilization would bring ethical and practical challenges. Should we try to communicate? Would we be prepared to deal with cultural, technological, and even physical differences? What if they are not friendly? Another crucial point is the psychological impact. For many, the idea that we are not alone can be both exciting and scary. Religions, political systems, and cultural identities could be deeply affected by the revelation that we are only a small part of a vast and diverse universe. Preparing us for the unexpected, whatever the scenario, finding life in TOI-700 and would change our perspective on the cosmos and about ourselves. We need to be prepared to face the consequences of this discovery, whether grand or modest. This includes investing in scientific research, creating international protocols to deal with extraterrestrial contacts, and promote a global mindset of cooperation and respect for the unknown. Scientists use simulations to predict what it would be like to live on a planet as TOI-700e. Longer days, different gravity and alien landscapes are some of the possibilities that these models help us imagine. Although we do not yet have concrete data on the exact conditions of TOI-700 and simulations, based on their known characteristics, such as size, orbit, and star type, allow us to visualize the future of a possible colonization. This chapter presents futuristic views on what our life would be like on this distant planet and explores whether we will adapt or create new forms of existence. Longer days and stable climate. One of the first remarkable differences between TOI-700 and Earth is the length of the day. The planet completes an orbit around its star every 37 terrestrial days, but that does not mean that the days there too much. If TOI-700 and is locked by tide, that is, always showing the same face to its star, one side of the planet could be permanently illuminated, while the other would be eternally in darkness. This configuration would create extreme regions, a hot, sunny hemisphere with high temperatures, and another cold and dark, with intense ice and winds. However, the intermediate zone, known as the Terminator, could offer milder conditions, with constant light and dark cycles. This unique climate dynamics would challenge our traditional form of living. Humans would probably build colonies along this intermediate zone, where temperatures would be more stable. Agriculture, for example, would depend on advanced technologies to deal with variable sunlight conditions, such as adjustable solar panels or artificial lamps to simulate the day cycle. Different gravity, a new sense of movement. Gravity in TOI-700, and although probably similar to Earth, could have small variations that would affect our body and behavior. Even a difference from few percentage points could impact everything, as we even walk as our muscles and bones respond to the environment. In a slightly lower gravity scenario, physical activity would require less effort, while greater severity could cause muscle fatigue and long-term health problems. In addition, physical adaptation would be just part of the challenge. Our sense of balance and coordination could be changed, requiring specific training before any attempt to colonize. Equipment and structures would also need to be redesigned to support local conditions, from vehicles to housing buildings. Alien landscapes, a strange and wonderful world. Imagine the landscapes of TOI-700, and it's like painting a picture of a completely new world. Under the fine light of the red dwarf TOI-700, the sky could have reddish or orange tones instead of the vibrant blue of the Earth. Alien plants, if any, could have unusual colors, perhaps black or purple, to maximize the absorption of weak light emitted by the star. Mountains, oceans, and even clouds could have different shapes and compositions from those we know, creating a surreal panorama. These landscapes would not only shape our sensory experience, but would also influence our culture and psychology. Living in such a different world could inspire new forms of art, architecture, and philosophy, reflecting our adaptation to an alien environment. However, this change could also generate feelings of isolation or nostalgia on the Earth, especially in the first generations of settlers. New forms of existence, adaptation or transformation. Will we adapt or create new forms of existence? As we face the TOI-700 peculiarities, and it may simply adapt using technology, artificial habitats, synthetic foods, and protection costumes. However, a more radical possibility is that we evolve biologically or technologically to better integrate into the environment. For example, bioengineering could be used to genetically modify human, making them more resistant to the specific conditions of TOI-700e. More efficient bodies to deal with different severity, radiation-resistant skin, or even expanded cognitive capabilities could come true. Alternatively, man-machine mergers could allow us to transcend our biological limitations, creating a new form of hybrid existence. Another approach would be to transform the planet itself through earthworking. Processes such as induced global warming, release of atmospheric gases, or introduction of modified organisms could change TOI-700 and to become more like Earth. However, this would take centuries or millennia and raise ethical questions about the impact on existing alien ecosystems. A future full of possibilities, living in TOI-700, and would be a profoundly transformative experience, full of challenges and opportunities. Simulations and models help us glimpse this future, but reality will probably be much more complex and surprising than we can imagine. Whether adapting to the alien environment or turning it to meet our needs, one thing is certain: our journey to TOI-700 and will change who we are as a species. TOI-700 and is not the only candidate for space colonization. Planets like Next Centauri b and TRAPPIST-1 and are also on the list of potentially habitable worlds, each with its own promising characteristics and unique challenges. This chapter compares TOI-700 and with other exoplanets that could be our next home, exploring whether it really is the best candidate or if there are more viable options in the cosmos. Proxima Centauri b, the nearest neighbor. The main advantage of Next Centauri b is its proximity to the Earth. Located just 24 light-years away, it is the most habitable exoplanet next known. This proximity significantly reduces the logistics challenges of an interstellar mission, allowing faster, albeit limited, communication and reducing the time required to send human probes or crew. However, Near Centauri b has its own problems. It orbits an extremely active red dwarf star, Near Centauri, which emits intense sunscreen and lethal radiation. These events may have worn out or even completely eliminated the planet's atmosphere, making it inhospitable to earthly life forms. In addition, there is evidence that the planet may be locked by tide, with one side permanently focused on its star and another in eternal darkness, creating extreme heat and cold conditions. Although its proximity is tempting, the risks associated with radiation and unstable weather conditions make it a risky Centauri B near comparison with TOI-700e. TRAPPIST-1e, a system rich in possibilities. The TRAPPIST-1 system is another strong competitor, with 7 rocky planets, of which 3, including TRAPPIST-1e, are located in the star's habitable zone. This abundance of promising candidates makes the system a priority for scientific studies. TRAPPIST-1, and in particular, seems to have characteristics that make it suitable for sustaining liquid water and possibly life. However, as well as next Centauri B, the planets of the TRAPPIST-1 system face challenges related to star activity. The host star, TRAPPIST-1, is another red dwarf prone to intense solar explosions. In addition, the orbits of the planets are very close to each other, which increases the risk of gravitational interactions and climate disturbances. Another critical point is the distance, about 39 light-years from Earth TRAPPIST-1, and is much further than next Centauri B, but even closer than TOI-700e. Despite its promise, the TRAPPIST-1 system has uncertainties similar to those of other exoplanets around red dwarfs, especially with regard to atmospheric stability and radiation protection. TOI-700e, the best candidate? So TOI-700 really stands out as the best candidate for colonization, compared to the next Centauri B and TRAPPIST-1, and it offers an intriguing combination of advantages and challenges. Its location in the habitable zone, its size-like size, and the relative calm of its host star TOI-700 are significant positive points. Although it is still relatively distant, 100 light-years, the stability of the system and the evident absence of extreme star activity suggests that TOI-700 may have more favorable conditions to develop and maintain a dense atmosphere and stable ecosystems. In addition, its intermediate position in terms of distance, not as close as close Centauri B, not as far away as other systems,